Great. So next up is Mihai, and I guess Noah's going to join you. Right. Very good. Thanks.
Thank you. Hello, thank you. I am Mihai Maruseac, or to paraphrase Taylor Swift, it's Mihai, and I'm the speaker. And Noah has been my intern over the summer, and he implemented most of this work. So what are you going to talk about is securing your Bazel artifacts using SLSA. And let's basically go first through the problem and then how to solve it. So let's say we have two people, Alice and Bob, like typically in cryptography, A and B. And Alice is developing software, Bob wants to use it. So the animation, it's already there. And by luck, the software that Alice develops is exactly what Bob wants to use. So Bob decides, instead of re-implementing the wheel and spending time and so on, he's just going to use whatever Alice develops. But there is also Mallory, exactly like in cryptography, that tries to own Bob. So let's see how this goes. In order for Bob to use the software that Alice develops, there is actually a pipeline. Alice writes the code. This code gets put into some source repository, let's say GitHub, but maybe somewhere else. From there, you get some dependencies, combine everything together into a build, so you create a final artifact. This artifact, in general, is deployed to somewhere, for example, on PyPI or on a GitHub release page or NPM and so on. And then this artifact gets downloaded by Bob and used as part of their build process, as part of their infrastructure in their production, and so on. So let's actually start with a very simple example. I selected C++, a very small source code that just prints hello from C++ and uses FMT as a dependency to print 42. And a very simple build rule. All of this is simple. So this is the code that Alice wrote, and it builds with Bazel. Bob wants to use this code. So Alice pushes this to a GitHub release. Let's just simplify everything and make it a GitHub release. Pushes it there, and just to simplify the life for Bob, it also pushes the binary directly into the assets. So now Bob comes to this page, sees that hello is here, and just downloads it and starts to execute it. What could go wrong, right? Well, Bob got pumped. So how does this happen? Bob panics, starts to look at the incident, tries to understand what happened. He looks at the release page, he sees the commit, he goes on the GitHub source code, he looks at the same commit, the code there looks right. So what could have happened? Actually, if we look closer, we see that the release has been done at some point in time, but the binary has been updated much later. So actually what happened here was Mallory had access to the GitHub organization, so he could modify the release page. So Mallory just created a malicious binary, uploaded it to the release page, and waited until Bob downloaded it and pawned Bob. So this is a typical scenario of an insider risk where somebody that has elevated access can exploit the access to then stage an attack later. Okay, so how do we solve this? One simple solution is to add a signature to your binary. But in the case where we have an insider risk, the insider can also push the signature there. So it's not really helpful, especially since most users would say, oh, I have this binary and it's already signed. It's all good. I can go with that. In order to solve this, the first thing is automate the release process. So instead of having a user start the release, then build the binary on their own laptop and then upload it, make everything automatic, and then give access only to the automation to do the upload of the artifacts. This already reduces a lot of the insider risks, because now, in order to modify the binary, you would need to perform extra steps. What extra steps? Let's go back to the diagram. Instead of just compromising the build repository or tricking Bob to download the bad artifacts, now if I automate the entire release process, I will have to compromise the build process itself or the deployment stage. So I'll have to add attacks way ahead in the scheme. Okay, so let's go back. Let's automate the release process with GitHub Actions, because I'm just using GitHub. It's simple. I just do a workflow where I run Bazel build inside the workflow. And then I also have another step where I upload the artifact to the release page. And if I do a release like this, now there is 5 minutes ago, the binary got updated, is exactly when the release tag got created. All is good. So now Mallory is not able to modify this because he no longer has access. However, we are not done yet. As I was saying, there are still avenues of attack. Like you can see in this diagram, Alice could, by mistake, submit bad code, or a dependency might be vulnerable, or an attacker can actually compromise the build control, the build process, and alter the CI/CD, and so on. And this is actually something that happens. And this is an example. Let's say somebody sends a helpful PR to your organization, to your repository, and in the thousands of lines of code, there is also this thing. In the CI, they just download something from somewhere on the internet and immediately pipe it into Bash. The CI passes, maybe you don't notice this line, or maybe you notice it, you look at the URL, and at the time it's a really useful dependencies, that's something useful. But this URL is owned by the third party. So at some point in time, they might just deploy malware. Malware is going to run on your CI, is going to change whatever artifact you are releasing. Then they can immediately replace the URL and make it serve regular stuff. So now you still get owned. And this is not theoretical. This actually happened. You might want to take screenshots to look at those QR codes for more information, but this actually happened for the SolarWinds attack. They basically got owned because the build system got compromised, and 18,000 of 300 customers got compromised. And in their postmortem, basically, they said two things. The first thing was that they needed reproducible builds. So once you have a binary, you could rebuild it somewhere else and check if the two binaries are bit by bit compatible. And this would detect compromise. The other one was you can use SLSA to protect the supply chain. So what is SLSA? SLSA stands for supply levels assurance for security. It's basically several levels that protect your supply chain. And it's going to protect all of these highlighted avenues of attack. So it's going to protect compromising source control, it's going to protect bypassing CI/CD, and so on. How does it do that? The general idea is that as you are building artifacts, you are also generating a provenance. Basically, you are saying this artifact has been built from these materials using this build process. So somebody said yesterday that Bazel is working towards generating SBOMs, mentioned also the executive order from the US 14028. So SBOM is more like a list of ingredients that the software contains, whereas SLSA is more like the recipe. It's how you combine those ingredients to get the final artifact. And as I was saying, there is at the L in SLSA stands for levels. That is because there are 4 levels. Level 0 is the default where you basically don't guarantee anything. Anyone can do a release, can do whatever they want. Level 1 is just you write somewhere, this is how I build a package. So it could be either just the release workflow that we just saw before, or it's actually the SLSA format that just says, I build this package and that's all. And now level 2 and level 3, those are the more important ones. Level 2 basically guarantees that once you build a binary, it cannot be tampered after the build. So as long as it conforms to the provenance, it hasn't been tampered after you build it. Whereas level 3 is you cannot tamper the binary even during the build itself. So the goal is to get SLSA level 3 for all of the builds. So how does this work? Instead of having just one single workflow for the entire CI/CD system, so instead of doing the entire build yourself, you are going to delegate to a reusable workflow. This reusable workflow is in a separate repository. The guarantee is that an attacker cannot control both repositories at the same time. So as long as you trust the external repository, the SLSA builder, the SLSA framework repository, you are guaranteed that the provenance that that repository is generating cannot be tampered by an insider or by somebody abusing your CI/CD. And the general idea is in your workflow, in your GitHub Actions workflow, you are saying, I want to build these artifacts, and I'm cloning the code, I'm wanting to build this one. After you build them, you are saying to the reusable workflow, generate a provenance for that. GitHub calls the separate workflow and gives you back both the artifact and the provenance as a file. And then you can attach them to your release page. Okay, so now there are two ways in which you can generate provenance. One is to use a generic builder that already exists, or to use a builder that is specific to the build framework or to the language. In general, using the specific builder is easier because it's already implemented. You don't need to do anything. You just call that, and that's all. The problem is the generic builder, because it doesn't know what you are using to build, it can only prevent tampering after the build. It's still during the entire CI/CD that you are doing for the release, but your provenance is only after the binary has been built. Whereas if we use a specific builder for Bazel or a specific builder for C++ and so on, the builder itself has visibility into what you do for the build. So it knows all of the steps, all of the parameters, and it can record them in the provenance. So basically, this gives you a bigger guarantee that the final artifact has not been tampered with. In order to do the Bazel-specific builder, you need to implement this. So you need to send a PR to the SLSA team to implement the builder and so on. Or there is the possibility to have the SLSA team create this for you. And the solutions that Noah picked is something that combines the benefits of both a generic builder and the Bazel-specific one. Basically, we are using a bring your own builder approach, where instead of you delegating the build to the SLSA repository and that repository will do all of the work for you, now there is a second level delegation that happens behind the scenes. So here on gray, on project workflow and tools and outputs and attestation, that is me as the repository owner. So let's say I create a tool and I want to use SLSA for that. And everything that is in the middle is what's happening behind the scenes on the SLSA side. So in my GitHub Actions, I'm saying I want you to build this artifact. So I want you to build these targets, Bazel build // ... for example. And then the SLSA Bazel builder behind the scenes would first connect would run a specific workflow to get a token, to get a signature and so on that we'll see immediately later. And then we'll use that token to run a reusable workflow that would run Bazel build with whatever targets I specified. During this time, it will record all of the dependencies, all of the arguments that you have used for the build, including optimization flags and so on. And then we'll give you back both the artifact and the provenance file. So how does this look? When I do the release page, I have the asset, the hello binary, and I also have this intoto.json file, which is basically a JSON file that is the provenance. So let's look a little on what this file contains by itself. It's a JSON, so I'm going to use JQ to print its content. And we see that it has a payload with a specific type and some signatures. It can have more than one signature, but in general, you'll see just one of them. So behind the scenes, there was a payload that got generated that basically contains information about the build. And then this got signed, and this signature is stored in a transparency log. If you want to find more, this transparency log is monitored by Sigstore. So you can check whatever has been signed by you. Other people can check whatever has been signed during this period of time, and so on. Okay, so the important part that we want to look at that depends from build to build is the payload. So now let's look a little bit more into the payload itself. The payload is a base64 encoded string, so I'm going to decode that and then look into that JSON using JQ again. So one of the fields there is the subject, which is basically the binary that I built. So you see it's Bazel bin source hello, it's the binary, and a checksum. So if somebody changes the checksum, gets access to the release page and changes the binary, that checksum won't match. So if they want to hide their tracks, they'll have to generate the entire provenance itself. But because the provenance is signed, they'll have to also sign it again. But the signature is stored in a transparency log. So now you'll see somebody that monitors the log would see that there are two different signatures, signing events in the transparency log for the same binary. So this could then raise an alert, and then somebody can detect, okay, there was a malicious insider here. Let's act on that. The provenance actually does more than that. So beside the subject, it also records the builder. So in this case, it says it's a Salsa framework builder at that specific version. So even if you don't trust the Salsa builder, or maybe the builder itself has been malicious, you can look at the provenance and detect, okay, I need to rebuild my stuff because this builder has been malicious or the builder has been compromised. Now I can detect whichever of my binaries have been using that builder so that I know to either rebuild them or remove them from organization and so on. It also records in materials, it records all of the dependencies that you have used. In this case, because it was just a simple binary, it only records the repository. And by the repository, it also records like what commit have I used and what was the tag. And this one is the repository, more details into that. You can see the GitHub reference and the commit where I did the release. There are a few more fields into the provenance, but in general, you don't want a human to look at them. You want this to be automated. So basically, the idea is that the provenance is kind of useless if it's not verified. And in general, when you download something from the internet, if it has a signature or if it has a provenance, that's not enough. You also need to verify that. So like if you have a GitHub action that says install some dependency, immediately after that, you should verify the provenance, or at least the action itself should do it for you. Okay, so how do we verify Salsa? Fortunately, there is the Salsa verifier that can be also put in a GitHub action. It's just a single command that you would run and will tell you if the provenance matches the binary. And I will also have an example for that. It is like this. So I pass as argument the artifact .fib, for example, and I pass the provenance path, and it verifies it. It tells me it has been verified. This was the generator. This was the commit where it was built. The provenance passed. You can put this into a GitHub action. If the provenance fails, stop the build there, and there is an alert, and so on. Basically, integrate it everywhere in CI/CD and work with that. Okay, so now moving back to the Bazel builder, because Bazel supports multiple languages, if your project builds, let's say, C++ and Python together with Bazel, you can generate Salsa provenance for that without needing to have a custom Salsa builder that would work, that would know how to mix Python and C++. So basically, everything can be done just with the Bazel builder. And if you use this, you have the nice benefit that all of these attacks are prevented. So now a malicious insider, even if they can get into your build environment, somebody that verifies the Salsa provenance can detect this. So SolarWinds most likely would not happen again if you properly generate Salsa. But there is more. There is an alternative called Salsa Rebuilder. If you remember from the SolarWinds postmortem, they had two ideas. One was to use Salsa, the other one was to do reproducible builds. So what is the idea behind the rebuilder? Let's assume that you don't have visibility into the workflow of one of your dependency, but that dependency is critical and you cannot replace it. And maybe you don't completely trust their developers, but you really need to use that dependency or spend years of work to re-implement it. So what you can do with the rebuilder is have a separate build process that would try to infer the build system, and then taking the source code and the artifact would try to rebuild it. So now you have two artifacts, the artifact that was released by the external party and the artifact that your rebuilder built. If these two are matching bit by bit, then you know for sure that you can trust the build. And actually you can generate a Salsa attestation that says this artifact has been rebuilt and it works. This is the work that in general the Salsa team is doing now for OSS rebuild, for trying to rebuild the entirety of the open source ecosystem. So for example, of the top 100 packages on PyPI, where you don't know how they have been built, and you cannot go back in history to find out where they have been built and insert Salsa for them, the OSS rebuild is going to rebuild them and then generate a side attestation that says, we have rebuilt this and it works. It's guaranteed that the build has not been compromised. So what Noah did was trying to do a Bazel rebuilder that would take an artifact, would take the provenance, and would try to rebuild it. And then will tell us if the rebuild matches the binary. And after he did that, he tried to use the rebuilder on several Bazel projects. and discovered that a lot of them were not exactly using Bazel in a way that benefited from hermeticity. For example, they were doing pip install and then Bazel build, or they were installing tool chains, they were installing a lot of dependencies using the operating system, so outside of the Bazel sandbox, and then they were using Bazel build. And this, of course, breaks reproducibility. So the next step is to actually motivate the developers to either use hermetic builds with Bazel, or to work more on the rebuilder to take into account the operating system and everything else that got installed as a side. And that is all that we can do for today. So now we can stop for Q&A.
Why don't we start with Julio? We'll fix the mic.
Yeah, hello. So you mentioned GitHub Actions to run this check, but I wonder when you use a GitHub action, there is no validation that what you downloaded was trusted or anything, right? You specify a version number and that's it. There's no check and validation that the thing you're downloading to actually verify later something else is trusted.
So the provenance itself contains both the tag and the commit hash where the GitHub action was run. So if I go back to this one, I have both the tag and the commit recorded in the provenance. So even if you change the tag later to a different commit, the provenance will no longer match.
Oh, but you showed the tool later to verify this, right? The tool that you run in the GitHub action, that binary is downloaded by the GitHub action itself. And you don't verify that this tool is the one you wanted.
You can verify because this one also has a provenance. So the SLSA verifier itself has its own provenance. And for that one, you either check a or it also has a signature. So you can check the signature for that. You can check the provenance, or you can just JQ into it and look at the specific fields. At some point, it's a reflection on trusting trust. At some point, you'll have to say, I trust this, and then from this, I build the rest.
I noticed that in version 0.1 of SLSA, source code review was included as a requirement, but in version 1, as released, it no longer is. I'm just wondering if you do have source code review, is it included in the provenance in version 1, or is it just for the future?
So I'm not exactly working on a SLSA team, so I don't know exactly the full decision for that. But the idea for SLSA 1.0 is that there is a build track that the provenance covers. So whatever we discussed so far is the build track for SLSA. And there is going to be a separate source track that would cover source review, repository maintenance, like you have branch protection and so on. That would come at a later time.
Other questions?
Just from the vocabulary, I was wondering, you mentioned this Bazel builder. Is that, I didn't really grasp, is that a different Bazel binary? Is that some kind of add-on Bazel?
It is an add-on to Bazel. So if I go back to this diagram here, you in your workflow, instead of saying, actually, let's go to this Bazel build command. So here, instead of saying Bazel build and the target that you want to build, you are just going to replace this with use the reusable workflow from SLSA that gives me the Bazel builder. And as an argument, you pass // ... I want you to build all of the binaries in my process. Or if you have a big repository and you have a top target, you are going to pass that top target.
I've got a question. Does the initial framework, the SLSA provenance framework, distinguish committed source code from committed but not properly released binaries? So if you just drop a binary in there and
yes, it's in the materials. It should record this is the code that is committed from the repository, so it deals with that. And if you're in CI action, you say download this from somewhere, and the CI knows to record this into the provenance. That binary can also be listed in the materials.
well, I actually meant a malicious just copying a binary into GitHub. Are you actually looking at the the attributes and so forth to figure out whether it's what type of artifact it is?
We're not looking into the binary itself. It's just recording. This has been the binary that has been used.
Okay.
That is the hash of it.
Got it. Okay.
So it's more for observability and transparency. It's not detecting malicious dependency. So that's why the inject vulnerability for the dependency is not highlighted in red.
Other questions? All right, well, thanks very much.
Thank you.
Space.